All right, good evening. Welcome to lecture number 3. Today, what we're going to do is look at inductive versus inductive arguments. That's one topic, and how to distinguish them. Also, we'll look at ways to assess them to see whether they're good or bad. And then we'll look at inductive generalization. So, sort of in a cursory manner, we'll look at inductive arguments in this first PowerPoint, but then we'll go more in depth in the second PowerPoint, and we'll look at how to critically evaluate and assess basically inductive generalizations, okay? So first of all, let's just talk, generally speaking, about the distinction between inductive versus deductive arguments. So I say on the slide here, the key difference between them is that with respect to inductive arguments, the arguer intends the premises to present probable support for the conclusion. Whereas in a deductive argument, the arguer intends that the premises should lend conclusive support to the conclusion, right? In other words, that if the premises are true, this necessitates the truth of the conclusion. So therefore, in some sense, inductive arguments are weaker than deductive. Inductive arguments only establish the conclusion of the argument with a degree of probability, whereas deductive arguments establish a conclusion with certitude, with 100% certainty, right? So that's the key difference between inductive and deductive arguments, all right? So I give you a couple of simple examples on the next slide. So if you look at the top argument, that's a deductive argument. Premise 1, 3 is greater than 2. Premise 2, 2 is greater than 1. It therefore follows conclusively with certainty that 3 is therefore greater than 1, right? Actually, that should be 1, not 2. That's a typo. Okay, so basically then, deductive arguments establish their conclusion with certainty. However, if you look at the argument below that, premise, all 100 squirrels observed in the park so far are gray, then I can infer that the next squirrel that I will see in the park will be gray. Now, notice so that that's a probabilistic conclusion. I can't say with certainty, maybe I'll run into a squirrel that is a different color, right? But I can say that given all 100 squirrels observed so far that they're gray, chances are the next one I'll observe will also be gray, okay? But notice that this argument is much weaker than the argument on top. The first argument is ironclad, right? If the premises are true, the conclusion necessarily must be true. Whereas the inductive argument is such that if the premises are true, the conclusion is probably true, right? So that's the key difference. Now, as I say, both arguments that I just gave you on the previous slide are reasonably adequate, right? The first is deductively valid, all right? This one up here, the deductive argument, and the inductive argument before is strong. If you see that many squirrels in the park, chances are the next one you see will be gray, right? So therefore, both are adequate in the sense that if the premise or premises are true, then in the case of the deductive argument, the conclusion will necessarily be true. In the case of the inductive argument, if the premises are true, the conclusion will likely be true. Okay, so I'm going to introduce you to a couple of terms here. A deductive argument is said to be valid just in case it is impossible for the premises to be true and the conclusion false. So that's basically what a valid deductive argument is, a successful deductive argument, in the sense that if the premises are true, the conclusion will necessarily be true. On the other hand, we have the term strong. For an inductive argument, it is strong just in case it is unlikely that the premises are true and the conclusion is false. So I saw 100 squirrels, they're all gray. Chances are pretty high that the next one I see will also be gray, but it's not a certainty, right? So that's a strong argument. So inductive arguments are strong or weak, and deductive arguments are valid or invalid, okay? So as I say here, not all inductive and deductive arguments are good arguments, right? So if a deductive argument where it is possible for the premise to be true and the conclusion false, then we call that deductive argument invalid, okay? So here's an example. Either it rains or it snows or both. It rains. Well, if it could do both, I certainly can't conclude that it doesn't snow. What I'm doing here is I'm treating the connective or as exclusive when in fact it's only inclusive. So then the premise could well be true, and premises could well be true and yet the conclusion could still turn out to be false, right? In other words, it could also snow. So that argument is a deductive argument, but it's invalid. Below that, we have an example of an inductive argument that is weak, where it is not, where even if the premise are true, it's not likely that the conclusion is true. So here's a good one here. 4 out of 5 dentists surveyed prefer Crest. Well, assuming you're just talking about 5 dentists and you've interviewed 4 of them, that's not a very strong argument, is it? Because you might interview another 20 dentists and they'll say the exact opposite, right? So therefore, that conclusion is a weak inductive argument. If the premise is true, it's still not very likely that the conclusion that most doctors prefer Crest is true. And moreover, we're talking here about dentists, but the conclusion is talking about doctors, which is a much broader category, okay? So the top argument then is invalid and the bottom argument is weak. So let's get a little bit of practice here, okay? So actually, so this is what helps you do the exercises, right? Is to work through some examples. So these are some inductive arguments, and we're going to try to figure out whether they're weak or strong, okay? So if you look at the top argument, 120 out of 135 engineering students interviewed on campus favor longer study breaks. Thus, most students on campus prefer longer study breaks, okay? I think you would agree with me that that top argument is inductively weak, right? Why? Because the premises are only referring to all engineering students, but the conclusion is referring to all students, which includes people majoring in various disciplines, right? So as I say here on the slide, the conclusion goes beyond the evidence. Therefore, it is not a strong inductive argument. It is a weak deductive argument, okay? So now if we made the conclusion weaker, we said, well, most engineering students prefer longer study breaks, then that wouldn't be such a bad argument. That would be an inductively strong argument. But if I go beyond the evidence and I say that all students are in favor of longer study breaks, and I think you would agree that that argument is weak, okay? So that's the first argument. So our verdict on argument number 1 is that it is inductively weak. Let's go to argument number 2, just below it. 120 out of 135 engineering students interviewed on campus favor longer study breaks. The margin of error was plus or minus 3% with a 95% confidence interval. In other words, what that means is 95% of the time, will be within 3 percentage points of the numbers that are cited in the passage, right? So those are pretty good odds. Thus, most engineering students prefer longer study breaks. I think we would say that that argument is stronger than the first argument, right? So the second argument, I would say, is inductively strong. Why? Well, first of all, it involves a margin of error, which tells us that the evidence is likely to be true, right? Because with a 95-degree level of confidence, your numbers will be within plus or minus 3 points, right? Percentage points. So that's pretty good evidence, right? Moreover, the conclusion does not go beyond the evidence, right? The evidence is talking about engineering students, and the conclusion restricts itself to engineering students. So we will say then that the second argument is inductively strong. Let's go to the one below that, okay? We know that the vaccine is more effective than the placebo in preventing the flu, since 73 in the placebo group contracted the flu, whereas only 65 people in the experimental group receiving the vaccine got the flu. Okay, well, here's the problem. The thing is that difference may not be significant, right? They're so close that it's possible that the difference could be due to chance alone. In other words, there are no inferential statistics. Like, for example, if this were a t-test, chances are it would not be statistically significant. So because the difference between 73 and 65 could be due to pure chance, then we really can't conclude with any degree of probability that the vaccine being tested is effective. Okay, so as I say here on this slide, it is therefore a weak inductive argument because the difference between the placebo and the test vaccine could simply be due to chance, right? There is no statistical inferential technique to justify the view that the difference is significantly significant, right? Therefore, and that's of course where inferential statistics come into play, but that is beyond the scope of this course, right? We're not going to do any inferential statistics in this course. Okay, so now we've seen the difference between, strong inductive arguments and weak inductive arguments, okay? Now, there are some further distinctions that I want to look at here regarding both kinds of arguments. Suppose a deductive argument is in fact valid. Does this in itself guarantee that the argument is a good argument, right? So consider the following argument. And I know it's a crazy argument, but premise one is the cup is and is not blue. So that's no contradiction, right? I'm saying the cup is blue and yet it is not blue. That's a contradiction. Therefore, the moon is made of green cheese. So you can see that the premise has no content relation to the conclusion. It's not even vaguely relevant to the conclusion. And moreover, the first premise is absurd because it's a contradiction, right? However, for an argument to be valid, it's impossible for the premises to be true and the conclusion false, right? Because the premise cannot be true, then it's impossible for it to be true and the conclusion false. So this argument then is valid. Why is it not a good argument? Well, so as I say here, the argument is, again, on the previous slide, is valid because it is impossible for the premises to be true and the conclusion false because the premise is a contradiction. It's necessarily false, right? Okay, now, regardless, even though the argument is formally valid, it is still not really a good argument because the premise is false, right? So we say then that the valid argument on the previous slide is unsound. It is valid, although it has a false premise. So again, just to review, the argument on this slide here is valid, formally valid. It's impossible for the premise to be true and the conclusion false because it's impossible for the premise to be true, right? So it is valid, but the premise is false. And because the premise is false, it's not a good argument, right? We say the argument is unsound. So an argument where the premises are true and the conclusion is entailed by the premises is said to be a sound argument. But if you have a valid argument where the premise or premises are false, then you have what is called an unsound argument. An unsound argument has false premises, even if it's valid. As I say here, a similar lesson can be learned regarding inductive arguments, right? Strong inductive arguments can be uncogent. So let me give you the following argument. 300 out of 400 groundhogs in the area can fly. Thus, most groundhogs in the area can fly. Well, we all know that groundhogs don't fly. We know that the premise is false. However, if the premise were true, then the conclusion would probably be true. If it really were the case that 300 of 400 groundhogs in the area can fly, then it really would probably be the case that most groundhogs in the area can fly. Now, as it turns out, it's still a bad argument. And the reason it's a bad argument is because even though it is a strong inductive argument, it is uncogent because the premise is false. So as I say here, it is clearly a bad argument, uncogent, because the premise is blatantly false. So some additional terminology then. An inductive argument that is strong and whose premises are true is said to be cogent. Remember what we meant by strong? An inductive argument is strong if it is impossible, if it's unlikely that the premises are true and yet the conclusion is false, all right? So that's called a strong inductive argument. However, if the premise is false, then it's said to be uncogent. If the premises are all true, then it's said to be cogent. So an inductive argument that is strong and whose premises are true is said to be a cogent argument, okay? Now, a deductive argument that is valid and whose premises are all true is said to be sound. Remember that a deductive argument is valid if it is impossible for the premises to be true and the conclusion false. If you have an argument like that and all of its premises are true, then we call that argument sound, okay? So four categories then. You have deductive arguments can be valid or invalid, all right? Also, deductive arguments can be strong sorry, deductive arguments can be sound or unsound. A deductive argument is unsound if either it's invalid or the premises are false or both, right? A deductive argument is sound only if it is valid and all the premises are true. This is a really good example, set of examples here that will help us to get a better grasp of the concept of deductive soundness and the concept of inductive cogency. Okay, so what I have for you here are three deductive arguments. All right, the first one is all ginger ales are white wines. Vernors is a ginger ale, thus Vernors is a white wine. Okay, now it would seem that that's a valid argument, but I think you would agree that it's unsound because the premise is false. It's not true that ginger ales are white wines. Okay, now look at the argument below that. All wines are beverages. Chardonnay is a wine, therefore Chardonnay is a beverage. Okay, now there, the argument is valid. It's predicate instantiation. Okay, and it is also sound because it is true that wines are beverages, and it is true that Chardonnay is a kind of wine, right? Now let's look at the argument below. All wines are a beverage. Chardonnay is a beverage. Chardonnay is a wine. That argument is invalid because the valid version of the argument would be all wines are a beverage. Chardonnay is a wine, therefore Chardonnay is a beverage. That would be okay, right? However, the second premise, or sorry, however, even though the premises are true, my apologies, the argument is still invalid. It's possible for the premises to be true and the conclusion false. Even if all wines are beverages and Chardonnay is a beverage, it doesn't follow that Chardonnay is necessarily a wine. It's possible for the premises to be true and the conclusion is false. So the final verdict then is that the top argument is unsound because although it is valid, it's predicate instantiation, the premise that all ginger ales are white wines is false. So this argument then is unsound. The second argument, all wines are beverages. Chardonnay is a wine. Chardonnay is a beverage. This is predicate instantiation. It's valid. Moreover, the premises are both true, and so therefore the argument is sound. The third argument below is unsound because the argument is invalid. Okay, so on the next, on the next slide, I give you, so on the next slide is what we just talked about, right? The first argument is unsound. Why? Although it is valid, it is an instance of predicate instantiation. Its first premise is false, right? Generally speaking, ginger ales are not wines, all right? What about the second argument? It is valid, predicate instantiation, and the premises are both true. So that argument is sound, okay? So clearly then, again, the top argument is unsound, even though it and the second argument are both valid. The premise in the first argument is false, so it's unsound. The argument below it is sound because it's valid and the premises are true. Then I talk on that slide about the third argument. As we said, it is unsound because it is invalid even though both premises are true, right? So there you have it then. So you have we had an argument then that's unsound because although it's valid, a premise is false. We had a second argument that is sound because it's valid and all premises are true. And we had a third argument that is unsound because even though the premises are true, even though the premises are true, the argument is invalid. Okay, so that gives you sort of an idea of assessing arguments, deductive arguments for soundness or unsoundness. Now what I have in the next slide is a group of three inductive arguments, okay? And what we want to determine for each of these inductive arguments is whether or not they're cogent. So remember again, going back to the definition of cogency, an inductive argument is cogent just in case, first of all, its premises are all true, and the premises strongly probabilistically support the conclusion. In other words, the inductive is strong, the argument is strong rather, and it's cogent because the premises are also true. Okay, so that's what cogent argument is. All right, so let's look at the top argument. Most ginger ales are white wines. Werner's is a ginger ale, thus it is likely that Werner's is a white wine. Okay, now let's think about that one. Okay, it says most ginger ales are wines. I don't think that's true. Do you? Werner's is a ginger ale. As far as I know, Werner's is a ginger ale, right? Thus, it is likely that Werner's is a white wine. It would be likely that it is a white wine, except for the fact that most ginger ales are not white wines. So therefore, the argument is inductively strong. If the premises were true, the conclusion would be also true. But the problem is that the first premise is false. So the first argument is uncogent. Okay, let's look at the argument below that. Most wines are made from fermented grapes. You know, that's generally true, right? I know there are people that make wines out of dandelions and other things, right? But a lot of wines, well, I'd say probably most wines are made from fermented grapes, right? Chardonnay is a wine. We know that's true. So it is likely that Chardonnay is made from fermented grapes. I think that's a pretty solid argument, right? I think you would agree that if the premises are both true, the conclusion is probably true. If it really is true that most wines are made from fermented grapes, and if it really is true that Chardonnay is a wine, then I think you would agree that it is likely that Chardonnay would be made from fermented grapes. So that argument is inductively strong, and it is also cogent because premise one, as far as I know, I'm not an expert on wines. Maybe for all we know, maybe more wines are made from other fermented things than grapes. But as far as I know, most wines are made from fermented grapes. So that premise is true. Chardonnay is a wine. That's true, right? So we have an argument where the premises lend strong support to the conclusion. And in addition, the premises are both true. So we say that the second argument is cogent. All right. Now let's look at the argument below that. Most wines are beverages. Werner's is a beverage. Thus, it is likely that Werner's is a wine. Okay, so most wines are beverages. I think you would agree with me that they are. As far as I know, wines are beverages, right? Unless they're frozen or something. Werner's is a beverage, right? Again, unless it's frozen, Werner's is a beverage. Okay, so those are true. It is likely that Werner's is a wine. I don't think that's very probable given the premises, right? Suppose it is true that most wines are beverages. Even if Werner's is a beverage, it doesn't mean that beverages, there can be a lot of beverages that aren't wines, right? So it seems to me that it doesn't follow with likelihood that Werner's is a wine, though Werner's is a beverage and even though most wines are beverages. So the argument is inductively weak. Now, granted, the premises are both true, right? But the argument is inductively weak. So therefore, we're going to say that the third argument is uncogent. Okay, so I summarize this on the next slide. Which of the following arguments is cogent? As we just said, the first argument is strong. If most ginger ales are white wines, and given that Werner's is ginger ale, then this makes it probable that Werner's is a wine. However, the argument is not cogent because the first premise is false. Most ginger ales are not white wines. Okay. Now, what about the second one? We agreed that it is, first of all, inductively strong. If most wines are made from grapes, and given that Chardonnay is a wine, it is pretty likely that Chardonnay is also made from grapes. Not certain, but it's likely. So it's a strong inductive argument. And as I say here, moreover, because all the premises are true, the argument is cogent. So this is an example of an argument that is inductively strong, and as such, the premises are all true. Okay? So that argument is cogent. Finally, the third argument. It's not cogent, right? So let's go back here. Most wines are beverages, Werner's is beverage. Both are true. But there can be a lot of beverages that aren't wines, right? So therefore, even though the premises are both true, it does not necessarily make the conclusion, doesn't even with probability, rather, make the conclusion true. And so therefore, it is a weak inductive argument, even though the premises are true. So we say it is also uncogent or not cogent, right? So finally, just to reiterate then, so argument number one on top is cogent. It's strong. Is uncogent. It's strong, but one of the premises is false. The argument below that is cogent because it is strong, and in addition, the premises are true. The argument below that, at the bottom, is uncogent because even though the premises are true, it is not a strong argument. Okay, so this then gives you some terminology that we use in logic and critical thinking. Terms like the distinction between deductive and inductive arguments, the distinction between strong inductive arguments versus weak inductive arguments, the distinction between valid deductive arguments and invalid deductive arguments, and the distinction between cogent versus uncogent inductive arguments, and the distinction between sound versus unsound deductive arguments. Okay, so these are all important terms that you should learn from this lecture, and I will ask you to apply it on the assignment. When I give you the assignment, when I post it next week, it will have some questions where I'll give you arguments, and I want you to tell me if it's inductive or deductive. If it's inductive, is it strong? Is it cogent? If it's deductive, is it valid? Is it sound? Right? So these will be the exercises. These are the exercises that I'll give you next week. Okay? So just to wrap everything up for this part of the lecture, know the distinction between deductive and inductive. Know the distinction between valid and invalid, and between strong and weak. Know the distinction between sound and unsound, and know the distinction between cogent and uncogent. Okay? All right. So, okay, so that's great. So that's the first part of the lecture. So what I want to do now is go to the second part. It gives us a closer examination of what are known as inductive generalizations. Okay, so those are used often in scientific inferences, right, in scientific research. So we'll stop sharing this one. Okay, and here I am. And now what I'm going to do is share another PowerPoint with you. I'll just have to track it down here somewhere. Oh, there it is. Yeah, inductive generalization. So there we go. Okay, so okay. Right, so hopefully everybody can see that. All right, so this is part 2 of the lecture. And in this second part of the lecture, what we're going to do is look at how you evaluate inductive generalization. So in the previous PowerPoint, we did talk a little bit about, strong versus weak inductive arguments. But we're going to sharpen our focus to what are called inductive generalizations. Basically, an inductive generalization goes from specific observations to general truths, right? Okay. And so what we'll do in this part of the lecture is we will consider several criteria for what would constitute a strong inductive generalization. Okay, so we're going to focus mainly on what constitutes a strong inductive generalization. We're not going to focus so much on cogency. We're going to get kind of more sharply focus on the concept of strong inductive generalizations. All right, so let's see what these criteria are for determining whether or not an inductive generalization is sound. Now, I'm sure you've heard this in practically any course you've taken, introductory level course. A sample being used to support a general claim should first of all be representative, right? Meaning that the demographics of the population are reflected in the sample drawn from it. So let's say I'm interviewing students at the University of Windsor, all right? My sample, and let's say that, I don't know, I'm just guessing, maybe, 40% take, social sciences, and maybe another, 40% take engineering or sciences, And so if I'm going to do a sample, if I'm going to do a statistical sample based on that demographics at the university, then I want to make sure that I have roughly 40% engineering and science students in my sample, and roughly 40% of, let's say, art students or social science students in my sample, right? So you want your sample to be representative. All right. Techniques to achieve representative include random sampling, stratified random sampling. So let's say that I want to do a political survey across all of Canada. If I want the sample to be representative, then I'm going to pick the participants randomly, right? And what should happen is that if you pick everything randomly, if you have a large enough sample, you'll end up with the demographics in the sample that approximates the demographics in the population. So first of all, then a good sample in an inductive generalization should be representative, okay? Something else too is that the sample should be of sufficient size in order to adequately reflect the population. If the bigger your sample, the greater the probability that your sample will be representative of the population, right? And there are formulas out there. This is beyond our scope in this course, but there are formulas out there to determine whether or not you have a big enough population, right? And so the more heterogeneous the population is, the larger sample required. So if I want to, let's say, determine how many Canadians are going to vote NDP or Green Party or Conservative or Liberal, whatever it may be, then what I want to do is make sure that I interview enough people so that I get a sufficiently large sample. And if I get a sufficiently large sample, it's also going to increase the probability that the sample will be representative, right? So these are just kind of common. I mean, we kind of know intuitively that you want a sample to be representative and you want the sample to be of sufficient size, right? Now, I'm sure if you followed any of the US election, you were bombarded with statistical polls practically every day, right? And if you're going to follow the Canadian election, you'll be, again, bombarded with statistical polls, right, when we get into the Canadian election. So in statistical polls, you have something called the margin of error. The margin of error of a confidence interval is the radius of a confidence interval within which you can be reasonably confident that your sample measurements reflects a population parameter. So let me just give you a simple distinction here. A population involves all the individuals you're interested in. So let's say I want to do a survey of Canadian voters. Then I'm interested in all 35 million Canadians, right? But obviously I can't interview all 35 million. So I want to take then a sample of that population that is representative, right? And I want to take a sample that has a low margin of error. So no matter what numbers I get, it's highly likely that the numbers I get are accurate, okay? So basically, when you're looking at a margin of error, how confident do you want to be that this is the case, that your margin of error is small and that your statistics will reflect what's going on in the population? This is called the confidence interval. It is the probability that your measurement lies within the confidence interval determined by the margin of error. So let's say my confidence interval is plus or minus 3%, right? Okay, if I have a 95% confidence interval, then that means it is 95% likely that my sample statistics will be plus or minus 3%. Those are pretty good odds, right? So you can have a lot of confidence then in a statistical study where the margin of error is, let's say, 3%, and your confidence level is 95%. That would be a pretty good sample, right? So again, it is customary. By the way, not all statistical polls, some polls try for 99% confidence level, but that's pretty hard to achieve. Most studies, at least statistical polls, go with 95% confidence level. So in a 95% confidence level, that means that 90%, 95% of the time, the actual population parameter will be in that confidence interval determined by the margin of error, okay? So the chosen confidence level, in part, determines the value of the margin of error. And another determinant of the margin of error is the sample size. The bigger your sample size, the smaller will be your margin of error, right? Okay. The lower will be the margin of error. You want ideally a fairly small margin of error. And there are actually formulas for, I'm not going to ask you to memorize these, by the way, or know these, necessarily for the midterm or the final, but how are the basic formulas for calculating the margin of error for a given poll? What are they? Okay, so I have some numbers on the next slide. The margin of error at a 99% confidence level is 1.9 over the square root of n, right? Where the square root of n, where n is the number of individuals in your sample, all right? The margin of error at a 95% confidence level is 0.98 over the square root of n, all right? Notice that the confidence interval for a 95% confidence level is wider than a 99% confidence interval. At a 99%, or sorry, it's the other way around, my apologies. The margin of error is wider for a 99% confidence level than it is for a 95%, all right? However, a 99% confidence interval is more precise than a 95% confidence level. So if I choose a 99% confidence level, although my my accuracy, although my sample will be fairly broad, it's not going to be entirely accurate, right? Okay, so the basic idea then, so let's just go through this again. So the margin of error at 99% confidence level is this here. What it means is that at a 99% confidence level, it is less, sorry, I should be the other way around. I guess I mixed up my terms. It's less precise, right? But it's more accurate, okay? More accurate because it's right 99% of the time. A margin of error at a 95% confidence level is narrower, all right? And so that means it's more precise, but it's less accurate. And finally, margin of error at a 90% confidence level is more precise, but it's less accurate still, right? So basically then, a 99% confidence level is more accurate but less precise. A 95% confidence level is more precise but less accurate than a 99%. And finally, a 90% confidence level is less accurate than a 95 or 99%, but it is more precise because the margin of error is much slimmer. So basically then, it follows that the large, now, okay, so that's one thing. So that's how you distinguish between a 99%, a 95%, and a 9%. What's good about a 95% confidence level, and sorry if I mixed up the terms a bit earlier there, is that you're kind of trading precision for accuracy, right? It's the best of both worlds. It's relatively accurate, but it's also relatively precise. It's not as precise as a 90% confidence level, but it's much more accurate. And it's not as accurate as a 99% confidence level, but it's still relatively accurate, right? And it is more precise than a 99% confidence level. So when you go from 99 to 95, you're increasing the preciseness or the precision, but you're decreasing the accuracy. When you go from a 95% confidence level to a 90% confidence level, you're trading in at that point accuracy for precision, right? Now, as I say below here, the larger your sample, the smaller will be your confidence interval and your margin of error. So if you just look at the formulas I gave you above there, you can see that the larger the n will be, obviously the smaller will be your confidence interval, right? Because let's say 0.82 divided by 10 is a much bigger quantity than 0.82 divided by, let's say, 100, right? So the smaller the n, the smaller will be your margin of error, okay? So generally speaking, when you're conducting a political poll, no matter what your confidence level is, you want to have a fairly large sample because the larger the sample, the lower is your margin of error, okay? Now, here's an example. Suppose I do a survey and I find that 45% of the respondents in a political poll favor the Democrats. Suppose I've chosen the standard 95% confidence level. My sample size is, let's say, 1,000. So what is my margin of error? So using that formula I gave you in the previous slide, it's 0.98 over the square root of 1,000. And the margin of error is 0.00309, in other words, 3%, right? So the confidence level at a 95%, at let's say a 95% confidence level is 45% plus or minus 3%. All right? Okay. So basically, so that's the confidence interval at 95% confidence level, plus or minus 3%. Well, that 45 rather, plus or minus 3%. Notice that if I use a sample with 2,000 individuals, then my margin of error is smaller. Notice that here, if you divide 0.98 by 44.72, which is the square root of 2,000, then you get 0.02. So now my confidence interval is narrower, right? At a 40, so it's got the same degree of accuracy, but now it's more precise because it's a narrower confidence interval. And so I'm more likely to capture the population statistics in that interval. So therefore, overall, the bigger the sample, the smaller the margin of error. And so the more precise is my estimation of the population proportion. Okay, so again, I think I messed it up on the previous slide, but let's just be clear then. So provision with respect to a confidence interval means that it's very narrow, right? Okay, because you're more likely to hit the bullseye, right, with a narrow confidence interval. But on the other hand, if your confidence interval is not that precise, but it's at a high confidence level, then it's going to be fairly accurate. So what you're doing is you're trading accuracy for precision. If it's accurate, then the chances are pretty darn high that your statistic will be in that the population statistic will be what your actual measured statistic is, right? So it's more accurate. So precision is good, but accuracy is also good, right? You want accuracy and precision. You want both at the same time. All right. And so again, the 95% confidence interval with a fairly large sample size is a good trade-off between accuracy and precision. It gives you a narrow confidence interval, so you'll have more precision, but it's at a fairly high level, namely 95%, so it'll give you a higher level of accuracy. Okay. Okay, now let's talk a little bit more. Let's go more in depth into the concept of population size. So I think you'd all agree, right, that if I'm doing, let's say I want to do a statistical study on campus about how many students support the NDP or how many students support the Liberals or whatever it might be. If I interview 10 students, you're going to say, well, McPherson, that's a pretty shoddy sample size, you know. I think you'd agree that I want to have at least, I don't know what, are there how many students on campus? Maybe 30,000, whatever it is. It's a mid-sized university. Maybe, you know, I'd probably at least like to interview 1 or 2,000 if I could, or at least, you know, at least more than 10 anyway, like maybe 500. It might not be too bad either. So the basic idea, so now we have to figure out when I'm doing when I'm doing statistical inference, how big should a sample be for a given population? Because again, I want my sample to reflect the population, right? I can't obviously, if I'm doing a sample on how many Canadians are going to vote NDP, I can't interview all of Canada, but I can maybe interview 500 people or 1,000 people, right? Okay. So therefore, how big a sample size should be depends on the confidence level and the desired margin of error. For very large populations, namely millions, often very small samples will do the job, right? The higher the desired margin of error, the smaller the sample size required. Okay. So basically, if you want a larger margin of error, let's say plus or minus 5%, then you don't need as many individuals in your sample, right? So the following table, the table on the next slide, can be used as a general guide for larger populations. At a 95% confidence level, the following are adequate sample sizes for the given margin of error. For populations of 15,000 to 2 million, plus or minus 2% margin of error, you need approximately 2,000 people to have an adequate sample size. All right? Okay. If at a plus or minus 3% margin of error, which is a little wider, right? Okay. A little less precise, you want approximately 1,000 people in your sample. For a plus or minus 4% margin of error, which is less precise, you want at least 600. So the smaller the margin of error, the more people or individuals that you need in your sample, right? So the basic idea then, again, is that the larger the sample size, the smaller will be your margin of error. And so the more likely that you're going to hit the bullseye, right? The more precise it will be. Okay, so what I want us to do now is to be able to apply what we've just learned on the previous 7 or 8 slides. I want to be able to apply this to some actual inductive generalizations. Okay, remember that an inductive generalization goes from several instances to a general truth, right? So inductive generalizations go from the specific to the general, from a sample to a generalization about not only the sample, but the entire population. So here's an example of a simple inductive generalization, okay? A survey of 2,000 students at the University of Windsor, randomly selected, indicated that 51% of them are liberals, okay? So the survey is accurate to within 2 percentage points 95% of the time. Okay, the reason we can have such such a low margin of error, right, is because of the fact that we have a fairly big sample, 2,000 students. You go back to the Gill research, it said, what did they say at the Gill research table? Was that the previous slide? Yeah, if you have 15,000 to 2 million, so we've got more than 15,000 students on campus, right? Then you need about 2,000 individuals to have a margin of error of plus or minus 2%, okay? So anyway, now, so again, I've interviewed 2,000 students at the U of W. I randomly selected them. Random selection helps to guarantee that the sample is going to be representative, that the demographics of the sample are going to be comparable to the demographics in the population. Okay. So anyway, let's say that I do an interview and 51% of the students I interview tell me that they're going to vote Liberal in the upcoming election. Okay. What can I strongly inductively refer? Now, remember, going back to the previous PowerPoint, right? We talked about strong inductive inference. And inductive inference is strong, such that if the premises are true, it is likely that the conclusion will be true, right? So what I want to determine is which of the following can I strongly inductively infer from the passage that we just read that's on this slide, okay? So let's go and look at our options. Number one, the majority of U of W students are liberals. Okay, remember, we said that the 2,000 students were interviewed, 51% said they were liberals. It's a margin of error plus or minus 2%. So the majority of U of W students are liberals, okay? So what do you think about that? Well, you know, frankly, I mean, you know, majority means 50% plus one. But if you look at the previous slide, right? If you look at the previous slide, the margin of error is plus or minus 2%. So it is possible that actually only maybe 49% of University of Windsor students are liberals or are going to vote liberal, right? Because it's a margin of error. So because it doesn't take into a margin of error, number one, we say is weakly inductively inferred because it doesn't take into account the margin of error. Look at the one below that. 49% of students at the U of W are not liberals. That also is weakly inductively inferred. Why? Because it too doesn't take into account of the margin of error, right? In fact, if the margin of error is plus or minus 2%, it may only be 40%, 7% of students at Windsor are liberal, right? So number two is also weakly inductively inferred. Okay, so far so good. All right, let's go to number three. 49% plus or minus 2% of U of W students are not liberals. Notice that 3 is an improvement on 2 because 3 is taking into account the margin of error. So 3 is strongly inductively inferred. Number 4, some U of W students are liberals. Well, that's pretty clear, right? I mean, you know, if I interview 2,000 students and 51% of those 2,000 say they're liberal, then I can at least infer that some of them are, right? That's a pretty, I mean, it's strongly warranted by the passage, right? So 4 is strongly inductively inferred. Let's look at number 5. Many U of W students, well, many doesn't necessarily mean 50% plus 1, right? Many means, I don't know, whatever, what, 20%, maybe 30%. Surely 5 is also supported by the passage, right? So what I'm saying is that this passage here supports both 4 and 5. Finally, we look at number 6. Most U of W students are liberals. Well, again, we can't infer that, right? That's kind of like 1. Basically, 1 says the majority are liberals. Basically, 6 is equivalent. It says most are liberals. We don't know that because the margin of error is plus or minus 2%. For all we know, 49% might be liberals, right? So therefore, 6 is weakly inductively inferred, right? So I summarize this on the next slide. The majority of UW students are liberals, weak, given it doesn't take into account the margin of error. Number 2, 49% of UW students are not liberals, weak, because it doesn't take into account the margin of errors. 3, 49% plus or minus 2% of UW students are not liberals. That is strong because it takes into account the margin of error. Number 4, some UW students are liberals. It's strong, even with the margin of error, right? It's certainly even 2 would be some students, right? Number 5, many U of W students are not liberals. It's 2 is a strong inference, even with the margin of error. And as we agreed, 6 is weak, given the margin of error. 6 is basically equivalent to 1, right? Most U of W students, you can't really infer that. If I say 51% of the students that I interviewed say they are liberals, but if my margin of error is plus or minus 2%, then for the population as a whole, it may only be 49% for all I know, right? So therefore, I cannot infer number 6 with a high degree of probability, okay? So the skill that we're learning right now is how to determine whether an inductive generalization is strong or weak, given the evidence in the passage, okay? So practice makes perfect. Let's try another example. A survey of 600 students at the U of W, randomly selected, indicated that 54% study every day. So I do a survey, maybe I talk to the students in person, maybe I send them a form to fill out on the email or whatever it is, but I surveyed 600 students. Let's say, just for the sake of argument, all of them respond. Normally they don't, but just to keep things simple, right? So let's say I interview 600 students, they all respond, right? And 54% of the 600 students I interviewed indicated that they study every single day, all right? 32% study 2 days a week, and the remaining 8% said they seldom study. All right. Now, of course, you could say, well, then you can't really infer anything from that, because for all I know, everybody's lying to me, right? How do I know that the 54% study every day? And I admit that, right? That is a potential flaw. But let's say, for the sake of argument, that everybody's telling the truth. Okay, just for simplicity, just for the sake of simplicity. Okay, so let's say they're all telling the truth, and 54% say they study every day, 32% 2 days a week, and so on. The survey is accurate to within 4 percentage points 95% of the time. So that is the confidence level is 95%, and the margin of error is 4%, plus or minus 4%. Then which of the following can be strongly inductively inferred? Okay, again, we're assuming that they're telling me the truth, right? So just, because otherwise none of these would be strong. Okay, so first of all, look at number 1. Most U of W students study every day. No, it's weak because of the margin of error, right? Okay, isn't it? All right. It's weak given the margin of error, because if it's plus or minus 4%, then for all I know, only 50% study every day, and 50% is not most, right? So that is weak given the margin of error. Number 2, at least half of U of W students study every day. That is strong, because the margin of error is plus or minus 4%. So that means even 50% study every day. That's still half, right? So number 2 can be strongly inductively inferred. It takes into account the margin of error. I can say with a strong degree of inference that at least half of U of W students study every day. Okay, let's look at number 3. Roughly a third of U of W students study 2 days a week. Okay, so what did I find out in my study? So 32% study 2 days a week. That's roughly a third, right? And even taking into account of the margin of error, it's roughly 32%. It's roughly two-thirds or a third. So we can say that that is strong. It takes into account the margin of error. So 4 can be strongly inductively inferred. Okay, now what about 4? On any given day, at least half of U of W students can be found studying at the library. Okay. Well, here's the thing. It may well be the case that, let's say, at least half of the students study every day, or at least they say they do, right? But maybe some of them study at home, right? Maybe they study at a cafe. Maybe, so not everybody that studies in the library, right? So therefore, it's a weak inference. I can't say with strength that that at least half of students study at the library. We don't know, right? So that's a weak inference. Number 5, roughly half of U of W students have fairly high GPAs. Well, Generally, if you study a lot, you're going to have a pretty high GPA, but it's not guaranteed, you know. Let's say you're taking a really, really hard course, you know, you're taking, I don't know, let's say you're in engineering, you're taking this really complicated engineering course. Um, you could study night and day and still not pass, right? So it's not guaranteed. So I can't infer with any degree of strength that roughly half of U of W students have fairly high GAs. It's weak because studying a lot simply does not lead to a high GPA. It could, but it sometimes doesn't. You know, I know about you, but when I was an undergraduate, I took this one course. I passed it. I don't know how the heck I passed it, but it was just crazy. It was just crazy, you know. And I studied hard for it, but it was really hard. So just because you study hard, it doesn't always mean you're going to get a high GPA. Number 6, almost all U of W students study at least twice a week. Okay. We don't, well, actually, no, sorry, I'm contradicting myself here. We actually do know this with a certain degree of strength, right? Given the margin of error. In other words, like I know that what is it? Around 32% study 2 days and 54% roughly. I mean, if you put those together, even taking the margin of error, I think it's strong. It's fair to say that almost all students, right, about 80% study at least twice a week. Okay, so that's strong. Sorry about that. It's not weak, it's strong. Number 7, some U of W students don't study. Geez, I don't know. You know, let's go back to the passage. Can we infer that with strength? The survey is accurate. Okay, so we know that. It says, and the remaining 8% said they seldom study. Well, here's the thing, right? 8% that say they seldom doesn't mean they don't study. You know, maybe they just study 1 day a week or 2 days a week, right? Well, or less than 2 days a week. Maybe they just study 1 day a week, or they study here, or they study there. That's not, that doesn't mean that they don't study at all. So therefore, number 7 is weak because seldom studying is not the same as studying. Okay. So what I will do for the next assignment is I'll put 1 or 2 of these on and just tell us what you think is strongly inductively inferred and what is weakly inductively inferred. Okay. The last topic of today's lecture is evaluating analogies. So I'm sure you've heard of analogies. So what exactly is an analogy, right? An analogy, as I say here, involves a comparison between two objects with respect to selected characteristics, where it is claimed they share at least one of these characteristics. Okay, so let's say I'm saying that a programmed computer, can solve math problems in the same way that a human can. Then I'm likening one thing to another. That's called an analogy. It involves a comparison between two things with respect to selected traits, whatever those may be, right? And it's claimed that they share at least one of these traits in common. It is then argued that if they share one of the traits, it is likely they share some of the other traits in common. So if I say that, you know, I know computers are like humans in the sense that they can solve math problems, and given that humans can think, then maybe it's likely that computers also think, right? So maybe if they share one characteristic with us, they share a second characteristic, right? So here's an example I have at the bottom of this slide, first example of an analogy. So it goes as follows. A government budget is like a family budget in the respect that both have lines of credit. Then governments can go bankrupt just like families. So what do you think? Is that a good analogy or a bad analogy? So let me go through it again. A government budget is like a family budget in the respect that both have lines of credit. Then governments can go bankrupt just like families. Okay? So what I'm saying then is that governments are like families in the sense that they have lines of credit. But families also go bankrupt sometimes. Then possibly governments can go bankrupt. So is that a good or is that a bad analogy? So what do you think? Well, it appears actually to be a pretty good analogy, isn't it? Right? Before we get into the formal criteria, I mean, if we're just sort of judging it off the cuff, it looks like a pretty good analogy. Yeah, of course, governments like families have lines of credit, right? The government of Canada as always operates or generally operates within a deficit. It's always borrowing money from other countries, right? Okay, so they have a certain line of credit, sometimes known as a debt ceiling. Okay, so and families have lines of credit, right? So let's say I bank with a certain bank, and if my credit is not too bad, they give me a so-called line of credit, right? So I can charge so much on my credit cards. All right. So governments then, I think, are like families in that respect. Then governments can go bankrupt like families. Well, certainly families can go bankrupt, right? And governments can too. For example, New Zealand went bankrupt. Across the river from us, Detroit. This is now going back maybe 15 or 20 years. They went bankrupt for a period of time as well, right? So governments can go bankrupt. So in other words, I think that's a pretty good analogy. Okay. But anyway, let's look into formal criteria for evaluating analogies. And before that, let's look at really, sort of I guess, the mechanics of analogies. All right. Analogical arguments, as I say here, generally speaking, have the following structure. Premise: A is like B with respect to some property X. Okay. Governments are like families in the sense that they have lines of credit. Families go bankrupt. B also has property Y. Things with property X tend to have Y. Things that have lines of credit also have the ability to go bankrupt, right? Therefore, it is likely that A also has property Y. It is likely that governments also can go bankrupt. So that's the structure of an analogy. A is like B with respect to property X. B also has property Y. Things with property X also have Y. It is likely that A also has property Y. Okay, so let's go back to the example from the previous slide. Premise: a government budget is like a family in the respect that it has a line of credit. Premise: families can go bankrupt. Premise: some things with a line of credit can go bankrupt. Conclusions: governments can go bankrupt. I think that's a pretty decent analogy. Now, obviously, you have to have ways of criticizing or critically evaluating analogies, right? So for analogical arguments, there are 4 ways to criticize them. Any argument with the structure discussed on the previous slide can be critiqued in the following ways. First of all, you can ask, does A really have property X? Is it the case that families have lines of credit? Yeah. Does B really have property Y? Okay. In other words, well, yeah. So, sorry, does A really have property X? In other words, do governments have line of credit? Yes. Does B really have property Y? Well, in other words, do families go bankrupt? Yeah, of course, right? Is the assumption that having property X is connected with property Y warranted? I think generally it is, right? Are there any relevant disanalogies? So this is an interesting one. Well, not really. I mean, I guess in some ways there's some disanalogies. For example, family budgets are much smaller than government budgets. In government budgets, we're talking about billions or even trillions of dollars. Family budgets are maybe what? Maybe 100,000, 50,000, something like that, right? So that's one difference. But again, I don't think that difference is going to really weaken the analogy. But that is something you have to consider. Are there relevant disanalogies between A and B that could weaken the analogy? All right. So those are 4 ways that you can use in order to criticize an analogical argument. And so that's really what we're learning in this section. Okay. So how does our example from the previous slide fare with respect to the criteria? Well, I've already gone over it with you, but I've got it here, so I might as well read it. It really is the case that governments have lines of credit. Of course they do, right? Most governments have debts, and most governments have what are called debt ceilings. And it is the case, unfortunately, that families sometimes go bankrupt, right? Sometimes, the credit cards are mount up and you just can't pay the debt, right? It does happen. Generally speaking, if someone has a line of credit, they can go bankrupt. If I have a $10,000 line of credit and I max it out, I could end up going bankrupt, right? Governments are bigger than families, as we just said, but otherwise the analogies hold. So, in other words, yeah, there's maybe one major difference. The government budgets are much larger than family budgets, but I'm not sure that that's enough to weaken the analogy. So I would say that overall, that was a pretty good analogy. Okay. Now, mind you, not all analogies are good. Some analogies are good and some analogies aren't. So, in the exercises that I'm going to post next Thursday, I will be asking you to look at a couple of analogies. Tell me if it's strong or weak. Tell me, if it passes the 4 criteria that I've laid out for you here on the slide. Okay, so let's go to slide 20. This is a really cool example. So I don't know if you've had me for other courses, but I teach a lot of ethics, right? I teach ethics of life, death, and healthcare. I teach animal ethics. I sometimes teach general ethics, 221. Sometimes I teach contemporary moral issues. So, I've been teaching ethics for a long time. All right. And sometimes what I do is in my medical ethics class, I teach the ethics of abortion, right? And one of the articles that we discussed, because it's such a good article, it's from Judith Jarvis Thompson. It's called The Defense of Abortion. All right. So now be careful, right? I am not, none of what I'm saying here about abortion reflects my personal views, right? This is just an excerpt from Thompson's article. And the reason I've put it here is because there's an analogy, and then we can together evaluate the analogy using our 4 criteria. Okay, so here is Thompson's first analogy. Suppose an ailing violinist requires to be attached to your circulatory system for 9 months in order to survive, right? So in the middle of the night, without your consent, the Society of Music Lovers attaches your circulatory system to that of the violinist. It's like, okay, and as Thompson goes on to say, this is like the case where a woman becomes pregnant without her consent. She says that just as the person is justified in detaching the violinist, the woman is justified in terminating the pregnancy, right? So what she's talking about are cases of pregnancy that are involuntary. And so she's saying that those cases are analogous to an ailing violinist. And she's saying that if you believe that a person has the right to detach the ailing violinist if it was done without their consent, then the mom has a right to detach the fetus if it was done without her consent. That's what the gist of the analogy. Okay. Now let's do an explicit analysis of the above argument. Let's put it into schematic form so we can verify that it's a bona fide analogy. Okay, so what follows in the analogy is the analogy made explicit. Okay, premise 1. A woman who has become pregnant involuntarily is like a person who has been involuntarily attached to an ailing violinist. I think that's right, at least in the respect that in both of your cases, it's been involuntary, right? You're keeping someone alive and you didn't ask for it, right? Premise number 2. A person who has been attached to the violinist can disconnect the violinist, which is morally warranted, right? So therefore, the violinist has property Y. Okay. So not everybody, by the way, would agree with this, but that's what she's saying. A person who has been attached to the violinist can disconnect the violinist, which is morally warranted because it was involuntary, right? Premise 3. Anyone who is involuntarily attached to another can, with justification, detach them. Conclusion: a pregnant woman can involuntarily detach the fetus. So that's an argument that Warren puts forward. It's an analogical argument, and it's against the strong argument that what is called the strong position regarding abortion, that abortion is never warranted because it involves violating a fetus's right to life. Okay, and that violating the fetus's right to life is murder. So that's basically the argument that she's trying to critically evaluate using this analogy, right? Okay. So again, just to go over it again, premise: a woman who has become pregnant involuntarily is like a person who has been involuntarily attached to an ailing violinist. A person who's been attached to the violinist can disconnect the violinist, which is morally warranted. Anyone who is involuntarily attached to another can, with justification, detach them. Conclusion: a pregnant woman can involuntarily detach the fetus. Okay? Does the analogy that we just discussed work? So what we're going to do now, and this is what I want you to do on your assignment when I post it next Thursday, use the 4 criteria that we mentioned above to assess the analogy. Number 1, a woman that has become pregnant involuntarily is like a person involuntarily attached to the violinist, right, in the respect that both are giving life to someone else. I think it's fair to say that condition one is passed, right? They're both giving life to another individual, they're attached to them, and the attachment was involuntary. So I think it's fair to say that the first condition holds. Condition number two. A person involuntarily attached, right, to an ailing violinist has a moral right to detach them. Well, is that true? I don't know. I mean, it's arguable. Um, you could say, well, I mean, if you're attached to the violinist and you detach them, they will die, and so you therefore have a moral right to keep them attached because each person has a duty to uphold human life, right? One might argue that. So two is a little bit iffy because not everybody agrees that if you're involuntarily attached to another being, that you have the moral right to detach them. So two is questionable. Three, generally speaking, it is not clear that someone who is responsible for someone else's life can give up that responsibility, right? So if I'm attached to the violinist, I'm responsible for their life. It's not clear that I have a right to give up my responsibility and detach them. Okay, so again, we're looking at those four criteria. The last one, remember, the fourth criterion is that there's an important disanalogy between the two cases. There's an important respect in which they differ, all right? Now, you could actually say that there is an important respect in which the two situations are different. The mother has an emotional attachment to the fetus, whereas the person that's attached to the violinist may not. Okay, so again, so the two biggest problems I think with the analogy is that it's not clear that you have a right to detach the violinist, and also there's a big difference between having a pregnancy and being artificially attached to an ailing violinist. Okay, so those are some ways in which we can critically evaluate the analogy. Okay, and that's what I want you to do on this assignment. I'll give you probably one or two analogies and ask you to evaluate them using those four criteria. I have a couple of other examples. All right, here's one at the top. Program computers like humans are able to solve math problems. All right, so I mean that's true, right? If you ever used a pocket calculator, that's a program computer, right? You can do all kinds of fancy things on them, tan and cosine and all this, all the trig functions, and that stuff. So I think it's fair to say that program computers like humans can solve math problems, right? Of course, we know that people can think, then it is likely that program computers can think. This is called the Turing argument, right? The idea that, well, computers can solve math problems like we can think, therefore it's likely that computers can think like we can, right? This is what all artificial intelligence research is all about. Analogy number two below. The universe is like a watch in the respect that it has a design, but the watch also has a purpose and hence a maker. Thus, it is likely that the universe also has a purpose and a maker. Okay, do you see the analogy there? So I'm likening the universe to a watch in the respect that both the universe and a watch have a design. But we also know that the watch having a design has a purpose. And if it has a purpose, it must have a maker. Then it is likely, says the argument, that the universe also has a purpose and also has a maker. By the way, in philosophy of religion, that's called the design argument or the teleological argument for the existence of God. Okay, so let's spell out the two analogies, right? Program computers like human beings can solve math problems, property A. Humans can solve math problems, premise 2, that's property B, right? Or property Y or whatever. Premise, anything that can solve math problems thinks, right? Therefore, computers can think. Okay, well, what do you think? Is it a good analogy or a bad analogy? I might put this one on the assignment. Let's look at the next one. This is the philosophy of religion example, the so-called teleological proof for God's existence, design argument. Premise, the universe is like a watch in the sense that both have a design, okay? Premise 2, watches have a purpose and therefore a maker, right? Anything that has a design has a purpose. conclusion, the universe has a purpose and a maker. What do you think? Well, it's debatable, right? Whether it's a good or bad analogy. It's regarded as one of the strongest arguments for the existence of God, right? Whatever kind of God you believe in, it's regarded as a fairly strong argument. Well, let's look at it. Let's analyze it a bit here. First of all, look at premise one. Is it really true that universes have a design? I don't know. Doesn't it kind of beg the question? If I say that the universe has a design, am I not already assuming that it has a purpose and a maker, right? It kind of begs the question. It assumes what it's trying to prove. And, it's not clear. Okay. Now, also, look at premise number 3. Anything that has a design has a purpose and a maker. Well, I don't know. Can there be things with the design that don't have a purpose or a maker? What about a rainbow? Why does a rainbow have the colors it does? It has to do with the fraction of light. It has to do with the ionization of water vapor. If you look at a frost in a window, was there some God that designed it? Or is it just that the frost in the window adheres to the rules relating to the chemistry of H2O, of water, right? So that one's not so clear. All right. So anyway, today we've learned 3 things. 1, we've learned how to distinguish between inductive and deductive arguments, between sound and unsound, between valid and invalid, between cogent, uncogent, strong and weak, right? And then we learned how to assess inductive generalizations, okay, using, criteria like margin of error. Is something warranted? Can it be strongly inductively inferred if it doesn't take into account the margin of error? Those are inductive generalizations. And then finally, we looked at analogies, right? Which, like in one thing to another in certain respects, is an analogy a good analogy or a bad analogy? And I gave you 4 criteria for determining that, right? And then what we did is we applied those criteria to several analogies together, okay? All right, so hopefully this is clear to everybody. And so I will post an assignment on Thursday, and in the next day or 2, I will post suggested exercises that you can go over with your GA in your respective labs. Okay, so have a great week, and I will post suggested exercises soon, and then later on Thursday I'll post assignment number 3. Okay, so take care. Have a great week.